The next test that we are going to talk about is called a ratio test, and the way it works is that if I have a series where the terms are positive, then I can look at the ratio an plus 1 over an. So I'm going to look at the ratio between the consecutive term in my series. Now you can imagine if this guy is less than 1, so what that means is my an plus 1 is going to be smaller than an. So that means the term that I'm adding to my series are gonna get smaller and smaller. So in this case, I would expect that my series should converge. On the other hand, if this guy is bigger than 1, so what that means is my an plus 1 is now going to be bigger than an, so I can move an to the other side here. So then that means the term that is being added to my series is only gonna get larger and larger, and I would expect my series to diverge in that case. And that is exactly what is going to happen here. So the ratio test states that if the limit of this guy, if the limit of an plus 1 over an, if it is less than 1, then the series is going to converge. However, if it is bigger than 1, then the series is going to diverge. However, if it equals to 1, then it is inconclusive. So I cannot say anything. The series, it may converge or may diverge. So let's take a look at the example here. I'd like to find whether the series here converge or diverge. So if I were to use a ratio test, I'm just gonna compute the ratio of an plus 1 over an and take the limit. So an plus 1 over an, if I look at this guy, my an is just 2 to the n over n factorial. So my denominator is just going to be 2 to the n over n factorial. And my numerator, I'm just going to replace n by n plus 1. So it is going to be 2 to the n plus 1 over n plus 1 factorial. So here, this is my an plus 1 over an, and now I'm going to take the limit of this guy where n goes to infinity. So the limit of this guy where n goes to infinity, the limit where n goes to infinity. So then let's compute this value. Now then, if I bring this thing to the numerator, I'm gonna get 2 to the n plus 1 over n plus 1 factorial times, I'm gonna flip this fraction here, so I'm gonna get n factorial over 2 to the n, and now things get cancelled out. Let's see, 2 to the n cancel out with 2 to the n plus 1, so I'm only left with 2. N factorial cancel out with n plus 1 factorial, so I'm going to be left with only n plus 1. So here, this is going to be just the limit when n goes to infinity of 2 to the n plus 1. And now you can imagine when n gets really large, I'm going to have 2 divided by a really large number, so that is going to be just 0. So, because this limit is 0 and 0 just so happen to be less than 1, so I can now conclude that this guy is going to converge. So this guy is gonna converge. So as you can see here, this test is going to work well when the terms in your series get cancelled out. So here we are lucky because most of the thing in my terms get cancelled out. So let's take a look at the next example here. If I were to use the ratio test, I'm going to compare an plus 1 by an. So I'm going to compute this ratio. My an plus 1, that is going to be 3 to the n plus 1 over n plus 1 squared. I'm going to divide this by a sub n, which is going to be just 3 to the n over n squared. And I'm going to take the limit when n goes to infinity. So this limit is just gonna be the limit of this guy. And once again, let me bring the denominator to the top. So I'm gonna get 3 to the n plus 1 over n plus 1 squared times n squared over, over 3 to the n. So let's see what gets cancelled out. 3 to the n cancel out with 3 to the n plus 1. So I'm gonna be left with 3. And I'm gonna have n squared divided by n plus 1 square. This doesn't get cancelled out, but I can pull out the square here, and I can pull 3 out of the limit. So this is going to be just 3 times the limit of, limit of n over n plus 1 square, where my n goes to infinity. Now then, when my n goes to infinity, n over n plus 1, this is going to 1. So I'm gonna have 3 times 1, which equals to 3. And now, because 3 is bigger than 1, so this is going to be in the second case. If the limit of a plus 1 over an is bigger than 1, then I can conclude that this guy is going to diverge. So that means I can conclude that this guy diverges. Now let's take a look at the next one. I have the series 1 over 3 to the n plus 2. In fact, we have done this earlier using the comparison test. So let's now try this again using the ratio test. If I were to use the ratio test, I'm gonna compute the limit of the ratio of an plus 1 over an. Let me just now go ahead and write the terms. They are going to be 3 to the n plus 1 plus 2 over a sub n, which is 1 over 3 to the n plus 2. Now then again, I bring the denominator up top, so I'm gonna get 3 to the n plus 2 divided by 3 to the n plus 1 and then plus 2. Now, I can divide both the numerator and denominator by, let's see, let me try 3 to the n. So then I'm gonna get the limit when n goes to infinity of 3 to the n plus 2 over 3 to the n over 3 to the n plus 1 plus 2 over 3 to the n. And this is going to equal to the limit when n goes to infinity of 1 plus 2 over 3 to the n divided by 3 plus, 2 over 3 to the n. Now then, when n gets really large, then 3 to the n is also going to get really large. So then 2 over 3 to the n is going to approach 0. And this guy, 2 over 3 to the n, is also going to be 0. So this limit is going to be just 1/3, which is less than 1. So, whenever the limit of the ratio between consecutive terms is less than 1, I can conclude that the series is going to converge. And this is the same conclusion that we have had earlier. So this guy is going to converge. Okay, let's take a look at the last one. This is just a harmonic series, so we actually knew that this guy is going to diverge. So let's try that using the limit comparison test here. I mean, not limit comparison test, the ratio test. If I use the ratio test, I'm going to compute the limit of the ratio between consecutive terms. So it's going to be this limit. I'm going to bring 1 over n up top, so I'm gonna get this guy now, the limit of n over n plus 1. Now then, this limit is just gonna equal to 1. And that's because I can divide by n on both numerator and denominator. So I'm gonna have n over n plus 1 over n, and this is just going to be the limit of 1 over 1 plus 1 over n. When n gets really large, 1 over n is going to approach 0. So this is going to be just 1. Now then, when the limit is 1, this is going to be in the third case now. Whenever the limit of the ratio of the consecutive terms is equal to 1, then the test is inconclusive. So in this case, using the ratio test, I can't really tell if this guy converges or diverges. So using the ratio test, it is inconclusive. But in fact, like I said earlier, we actually knew from using the fact that this guy is a harmonic series that it is going to diverge. So sometimes it depends on the test that you are using as well. Maybe you use one test and it doesn't work. So that means you have to try using other methods.